Hello, everybody. So today we're going to talk about continuity in behavior. So what we're going to look at here is we're going to determine if a graph is continuous or not, and then we're going to look at the three different types of discontinuities. And then we're going to look at, well, what about the end behavior? So as the graph leaves the grid, where is it going? Is it, going off into infinity? Is it approaching a specific number? What's happening there? Okay, so at this point, you should be able to sketch specific graphs with or without a graphing calculator, preferably without a graphing calculator. The ones that you're going to be required to know by heart is anything to the 0 power. So that's like y equals 7, y equals 15, y equals -3. Anything to the first power, so that's any of your linears like mx plus b, anything in that form. And anything to the power of 2, that's your quadratics. And so those three are the main ones that you're going to be for sure required to graph by hand. Now, anything that's higher than a 2, you will have your calculator you'll be able to use and be able to look at it that way. And then you're just going to have to transfer the information so that way you'll be able to go through and actually do the actual problems. So let's start about talking about continuity. The first thing we need to do is talk about polynomials. All polynomials are continuous. And if you're not really sure what a polynomial is, it's basically anything that is not a fraction or not a square root or something like that. It's like 4x squared plus 7 minus 3, 17x to the fourth plus 2x minus 1, things like that. Those are all considered polynomials. There are no fractions in them at all. They're not over anything in particular. They're just straightforward functions. When we talk about continuity or being continuous, that basically means that your function has no breaks or holes or any gaps in it at all. So there's no asymptotes, there's no holes in there at all. It just, you start at one end and you can draw the whole entire graph without picking up your pencil at all whatsoever. All right, so one condition for a function f of x to actually be continuous at a specific value is that the function must approach a unique y value, so a specific y value at that x value from both the left and the right side. So if you're trying to figure out, is this function continuous, you're going to pick a point somewhere, or it'll tell you what point to pick, and you're going to look at it from the left side and look at it from the right side to make sure that you are approaching the same thing, and then you're going to look at that actual specific number to see if that actual number exists or not. As long as those three things happen, then you have a continuous function. But the moment that you start approaching a value, and let's say you're trying to approach the y value of 7, and all of a sudden you stop at 5 and then you start going back down, then you're not approaching that number anymore from the left side, but as the right side approaches it, you are. And so you're not continuous when you actually hit that x value. So to show you what I'm talking about, we need to talk about discontinuities. So again, if you're not continuous, you're going to be discontinuous. And so there are three main types of discontinuities. The first one is going to be a hole. That hole basically means that we have a rational function, typically is what happens. And that rational function, you are able to cancel something out on the top and the bottom. And so the function, when you graph it, appears to be continuous, but if you actually zoom in on the number that you removed, there's actually a hole there. The other one's going to be called a jump discontinuity. This typically happens in piecewise, and it usually happens in absolute value. So when you have a jump discontinuity, we are looking at primarily piecewise, or we're looking at an absolute value. Usually that's where a jump discontinuity has here. The discontinuity again from the hold is usually a rational function. That's usually where this happens. Oops, function. The infinite one. So infinity basically means that you have an asymptote. So that usually happens when you have a variable on the bottom. So something in the form of this right here. When you have this, you're going to have a graph and you've got something that looks like that, where you have an asymptote that you're going to be running up against. And so that's where an infinity one comes from. So these are the three types of discontinuities that we're going to be looking at and determining or whatever. So talking about the first one, when you have a hole, you have a graph where you are not defined at one point. That basically means you've canceled something out in your graph, and because you've canceled something out, your graph still goes on, except when you get to that specific number, somebody took the manhole cover, so you have to jump over that little hole that's there. Okay, so that's what it means when you have a graph and it has a hole in it. Next one is your jump continuity. So this is usually, these are your piecewise functions here. So I spelled that wrong. Sorry about that. Piecewise. Thank you. So basically what happens is that when you get to this specific point here, you'll only have one point that will be defined, and the other point or points will not be defined. They'll have an open hole, and then one will have a closed hole. So when you look at something like this is called a jump because I'm going from here to here, or I'm coming from here to here, but I'm jumping to my next place. I'm not continuous. Now, not all piecewise functions are discontinuous, because you can have piecewise functions that will come in, and actually you might have this piece here might be an open dot because that's where we're ending. So on this part of the function here, we're coming up to this value, but we don't want to include that value. But when we start continuing on to the next piece, you can actually do something along the lines of this and make it graph like that. So that way, yeah, you had an open dot, but now we're actually going to include this same number that's in my new function. And so that actually closes it and makes it continuous because now you've connected it. But if you don't connect it and it looks like this right here, then you have a jump discontinuity. An infinite discontinuity basically means that you have a vertical asymptote. So remember, vertical asymptote means something has not been able to cancel on the top and bottom. And so you have a way for your denominator to equal 0. And so as you approach a certain x value here, you'll either run off into infinity, positive infinity, or you'll run down to negative infinity. Now, you can, depending on which side you're coming from, you can either approach the same infinity value from both left and right, or you can approach two different infinity values, one going negative and one going positive. So it's absolutely 100% okay to have something that looks like this or to something that looks like that. Okay? So this is fine if you have graphs and everything, but how do you tell from equations? Well, equations can be kind of tricky. So I'm going to show you just a couple examples of equations that show you that have discontinuities in them. So on the first one, your holes, you will notice here I have a hole, and I know this because this and this are going to cancel out. So I have a hole here at x is equal to 4, because if I take this x minus 4, set it equal to 0 and solve, that number makes it go to 0, and you can't have a 0 in the denominator. So I have a hole right here at that x minus 4. Now, You'll notice I still have this piece left over. We'll address this in a minute, but it doesn't cancel. But this piece right here basically says that I have an asymptote as well. So some of your rational graphs can have both holes and asymptotes. That is absolutely okay. The next one is going to be our, oops, I have a dot on my screen, is going to be our jump discontinuity. So basically here you have this function here. And so we're going to actually look at 1. So if I take the 1 and plug it into here, y equals 1 plus 3. And so that y equals 4 for the first one. And then do the same thing for the second one. Y equals 1 squared is 1 plus 4 times 1 minus 7. So y is equal to 5 minus 7, negative 2. So you'll notice that this value and this value are not the same thing. And because they are not the same thing, then we have to go through and get rid of, or not get rid of, but we have to basically describe it as being a jump discontinuity, because at that 1, I'm going to jump from my y equals 4 value with an open dot, because remember, there's no equal sign under that. So with an open dot, I'm going to jump down to my closed dot value friend of negative 2. So I've got something, I don't know, looks something at my 1 value. I've got something that kind of looks like this here. So my graph looks something like that, but you'll notice I have to jump down to that other value there. Okay. And then, so we have a hole, we have a jump discontinuity, and then so this other one is our infinite one. And so you'll notice here how nothing will cancel there. So that basically means if I was to draw this out and make this go x minus 3 is equal to 0, so x is equal to 3. So at my 3 value here, I actually have an asymptote. And my graph is going to probably do something that looks a little bit like that. Okay. So these are the 3 things that when you're looking at equations that you have to look for. You're might have to do some algebra to get these factored down, or you might have to do some evaluating to see if I'm actually continuous here. Because remember, I told you not all piecewise functions are discontinuous. They can actually be continuous in some of these piecewise functions, but that only happens when these 2 numbers are the same thing. If they're not the same thing, then you do not have a continuous function. And then you have your infinite over here. So you will hear infinite and jump discontinuities. Sometimes they're classified as non-removable. Basically, what that means is you cannot remove the actual point. Removable only happens when you have a hole, because you're literally taking out, you're canceling out something from the bottom and the top of this fraction to get rid of the that specific point. So that's your removable. Infinite and jump discontinuities are classified as non-removable because you're not removing anything. You're not canceling anything out. And as such, they are non-removable. So when you're looking at these and getting into that, if you see those specific words, just make sure that you understand the only removable discontinuity is your hole. The other ones are all called non-removables because you cannot remove anything from the actual equation. So what we need to do is we're going to determine whether each function is continuous at the given x values. Justify using the continuity test. If discontinuous, identify the discontinuity as infinite, jump, or removable. So removable means a hole. The continuity test is basically what you're looking for is, do your y values have the same number? If they don't have the same number, then it fails the continuity test, and you have to identify which one you actually have. So first thing, you know here that we can go ahead and get rid of the infinite one because there are no fractions. And since we have no fractions that have that are in this actual problem, these are both lines. We know that going forward, that's either going to be a jump or removable, or that actually could be continuous. So, oh, no, hold on one more time. Okay, I'm good. So what we're going to do is we're going to take this and we're going to focus on the -3 here. So I'm going to take the top one, 3x minus 2, and I'm going to plug in the -3. Nope, not equals. I'm going to evaluate that, and I get -11. Now, in order for it to be continuous, when I plug this one in here as well, I also need to get 11 back. So now I'm going to take the second one, 2 minus x, and I'm going to plug in my -3, and I get 5. So I know that my y values are not the same, so I know that I'm looking at a jump. We know that this is not removable because there's nothing here to cancel out with, so we know we can go ahead and get removable away as well. So infinite removable we're able to eliminate in the beginning. So now we need to basically look at, is it continuous or is it discontinuous via the jump? Is it jumping? Okay. So this is discontinuous. And the type of discontinuity you have is a jump. Okay. So that's how you would answer this question. We'll take a few moments, try this one, and then I'll hit pause, try this, go through it, and then when you have it done, unpause it, and let's see if you and I agree. So take a few moments to do this, and then hit play when you're ready. All right, welcome back. So I'm looking at this. Well, first off, I don't have any other restrictions over here. So remember, I have infinite. I have jump. And I have a whole, or I have removable. All right. So I have to evaluate it for this one and this one here. Well, I don't have any piecewise functions here. And since I don't have any piecewise functions, then I can go ahead and get rid of jump, because I know this is going to be a graph that I'm going to be graphing, but I'm not graphing more than once, so I don't have the opportunity to jump to a different y number. So it's either going to be infinite or a whole, or both, or neither. Okay, so if I'm looking at this, well, looking at it, I have no idea, but what I do know is if I plug in my -3 down here and my +3, I wind up with 0 in the denominator. So if you take a look, I'm going to plug in the first one, -3 plus 3, all over -3 squared minus 9. And I'm going to do the same thing for the other one. 3 plus 3 over 3 squared minus 9. I'm going to clean this one up, and I wind up with a 0 over 0. I'm going to clean this one up over here, and I wind up with a 6 over 0. So now I have two answers, and I have no idea what to do with them. Here's the good thing. You've done all the work that you need to. There's nothing else that you need to do. You just need to decide infinite, whole, or it's continuous. Well, we know that it's not continuous because you have a 0 here and here. Because you have that 0 here and there, it is not continuous. So you have some sort of discontinuity. When you have this right here, anytime you get 0 over 0, you have a hole. So if you go through this and you plug in and you get 0 over 0, you have a hole. So at x equals -3, you have a hole or a removable discontinuity. When you're looking at this one here, because I don't have 0 over 0, I have something over 0. You have an asymptote, so you're going off to infinity. So at x equals 3, you have an infinite discontinuity. Okay? So the easiest way to do this, plug them in. If you get this right here, 0 over 0, I don't care what the problem looks like. If you wind up with 0 over 0, you have a hole. If you wind up with anything else over 0, you have an infinite discontinuity, which means you have a vertical asymptote. All right. So what I want you to do now is I want you to go off into Delta Math, and I want you to try the continuity problems that are there. You just go in there, try those problems. I think there might be like 10 problems, and see if you have any questions after you do that. If you do, make sure you email me and you send me a reminder or whatever else, so that way I can see what's going on and I can help you out. If you want to go ahead and start your homework for these problems, you are looking at page 30, and it's going to be numbers 1 through 10. So that's what we just did here is problems 1 through 10 on page 30 from your online textbook. So you can go ahead and pause the video here and go out to Delta Math, or you can go ahead and go back to the link if you're on the Google Slides and select in behavior and go to the next one. Otherwise, I will hope to hear from you if you're having questions on this, or I'll talk to you in a second as we move forward. All right, so we are going to do in behavior. So in behavior, literally we deal with in behavior when we talk about polynomials. When we talk about polynomials, basically what I want to know is as my x gets bigger, what's happening to my y? Is it going off to positive infinity? Is it going off into negative infinity? And vice versa. As my x's go off to negative infinity, are my y's getting really big going off to positive infinity, or is it getting really small going down to negative infinity? So that's what you're looking at on here. Whether the graph of a polynomial eventually rises or falls, it's going to be determined by your function's degree, whether it be even or odd, and by the lead coefficient as indicated in the lead coefficient test. So here's what it is. If your n is positive and a is positive, then the graph falls to the left and rises to the right. So that's what we're talking about. So if your n is odd, so the biggest exponent in your polynomial, the highest exponent, if that exponent is odd and the coefficient sitting in front of it is positive, then your graph is going to look something like this piece here. If your n is odd, so your biggest exponent in your polynomial is odd, and your a is negative, then your graph will rise to the left and fall to the right. Notice I don't care about anything here in the center. I don't care what's going on there, not yet anyway. This is only dealing with in behavior. What happens after you are done on the inside and you're running off into going off to infinity or whatever? That's what I'm concerned about. If you're in, so the biggest exponent, if that is even, and its coefficient is positive, then your graph will rise to the left and rise to the right. And if your n is even and your coefficient for that exponent is negative, you will fall to the left and fall to the right. So these are the 4 different graphs that we're going to be dealing with and looking at, and these are the only 4 options and answers you're going to have. You're not going to have anything else. It's only going to be one of these 4. You're either going to fall left, rise right, rise left, fall right, rise on both left and right, or fall both left and right. Okay? This is just another way of showing it. And you want to talk about even degrees and odd degrees. It's just a different way of showing how it's actually going to go. But notice here the difference is we actually got this infinity. So this is where it gets kind of where you need to start paying attention. So as my x runs to infinity, my y is going off to positive infinity. As my x approaches infinity, my y is going to infinity, which means I'm going up. So this is a positive coefficient with an even degree. A positive coefficient with an odd degree. Mind you, this is the biggest exponent of your polynomial. As my x gets smaller, my y is getting smaller. And as my x gets bigger, my y gets bigger. Okay, so this is just a different graph that talks about what we just did on the previous slide. The only difference is this brings in your affinity pieces that you're actually going to have to deal with. So before you log into Delta Math and try your end behavioral problems, let's actually see if we can do a problem or two here. So we have negative x to the 4th plus 8x to the 3rd plus 3x squared plus 6x minus 80. This is your f of x. I want to know what is happening with my end behavior. Okay, so when I'm dealing with this, I want to only look at the biggest exponent term. So that's going to be this lead term. So I'm only going to look at this one here. All this other stuff can go away. I don't care about that. This is going to tell me what's going to happen with this graph. So I want to know, as x gets bigger, what's happening to my y, and as x gets, let's try that again, and as x gets smaller, what's happening to my y. So this is what I'm trying to answer, and I'm going to do this from here. So I know I have an even exponent. So if I'm going to go back, I know I'm going to look at specifically this column here. So I have an even exponent, and my coefficient, which is this piece right here, which sits in front of that x value, is negative. So you got to remember that this is really a -1 that is sitting right there. That -1 is sitting right there. So I have an even exponent and a negative coefficient. Oops, wrong way. So here's my negative coefficient down here. So this is the box I'm going to use. So my graph is going to look something like this. As my x gets bigger, my y goes to negative infinity. As x gets bigger, I'm sorry, there's actually supposed to be a negative right there. As my x gets bigger, my y goes to negative infinity. As my x gets smaller, my y goes to negative infinity. So my answer here is negative infinity and negative infinity. And we can look at that. Oh, well, that's not what was supposed to happen, but okay. We can look at that by this. So we come in here and we go to y equals. If you want, we can go ahead and put this big long equation in here. That's fine. Just move it up so I can actually look at it. So we have negative x to the fourth. Nope, didn't do that. To the fourth plus 8x to the third plus 3x squared plus 6x minus 80. And what I'm looking for are my end behavior points. Hit graph. All right, so I can't see anything. So I got to zoom this out. So we're going to go zoom 3. Oh, still kind of hard to see. Let's do it again. Zoom 3. Oh, now I can't see anything. So no, that's fine. Let's change our window. So let's go from -5 to 10. And we have a -80 as my y-intercept. So let's go for my y-min. Let's go -100. Oops, 100. And then come up to, let's leave it at 160 and let's go up by 50s and see what that does. Oh, there's that. And there's that. There we go. So we actually have a pretty decent picture. Let's see if I can fix that a little bit more so you can actually see what's happening. Let's go 300. No, that says 30. Second quit. Okay, keep going. Sorry about that. We'll go 300. There's a little curve going up, coming back down. Try one more time. If it doesn't work, then that's okay. We can just look at the graph. Oh, there we go. Now we have a picture of our graph. So if you're looking at this, this makes a lot of sense. So as my x is going off into positive infinity, going into that direction, you're going to notice that my y value is going down. So it's just going to keep dropping down further and further and further. So that's why we have this piece right here. As my x is going out to negative infinity, going out into this direction, all the way out here to the left as far as I can possibly go, my y values are getting smaller and smaller and smaller. And so that's why we have this piece right here. Okay. Let's try it one more time. Make sure you got it. So I'm going to write the problem down, then I want you to pause the video and I want you to see if you can come up with the lead coefficient test and see what we're actually going to wind up with, okay? So here is your problem. I want you to tell me the end behavior of this problem. So -1/4 x cubed plus 3/4 x squared minus 1/2 x. What I want you to do is use your lead coefficient test, and I want you to come up and tell me, as my x goes to infinity, what is my y doing? And as my x goes to negative infinity, what is my y doing? That is what I'm looking for here, okay? So pause the video, try it out, and then hit play and check your answers. All right, welcome back. So hopefully you've had a few moments, you've done this or whatever, and you didn't get too stuck. So again, we don't care about any of this. We only care about this one. Now, I wrote this problem here specifically because of how it's written. Because first off, it's in a fraction form. So you need to understand that, again, there's still that imaginary 1 that's sitting here. So what you're really looking at is negative 1 over 4 x cubed. Okay? So I know two things. I know that my exponent is odd and my coefficient is negative. So I'm going to go back to my chart here. We're going to get rid of all this. And that too. And that too. And I know that what I'm looking for is I am looking for odd. So I'm going to be looking for this area here. And I'm looking for, I have a negative coefficient. So that means I am looking for this box right here. So as my x's go negative, my y's are going positive. And as my x's are going positive, my y's are going negative. So if you did this correctly, you should get, as my x's go to positive infinity, I get negative infinity for my y's. And as x goes to negative infinity, I get positive infinity for my y's. And you can check this. So in your calculator, a second, y equals, so we're going to clear that out. Math, oh, wrong one. It just does not like me today. So we have negative x to the third all over 4 plus 3x squared all over 4 minus x over 2. Go back and go zoom 6, and that starts your window back at the traditional 10 by 10 window. And as you can see, it matches what we came up with. As x is getting bigger, my y's are getting smaller. And as my x's are getting smaller, my y's are getting bigger. So that's what you're going to be doing in this piece here. All right, so now what you're going to do is you're going to log into Delta Math, and you're going to try the in behavior problems. And then once you're done with the Delta Math problems, and if you don't have any questions, then you can come on to Google Classroom and you can start your homework that is now up. So the homework problems are again from page 30, but this time it's 22 through 29. That will be dealing with your continuity problems. And all you're going to do is look at the graph and tell me what's happening as x gets bigger and as x gets smaller, what's happening to those graphs. Okay. The other thing is you're also going to do page 31, and you're going to do problems 33 through, oh wait, let me change that. No. So you're going to stick with 22 through 29, and I will be putting something else up to do with this part, what we just did here, like problems like this. I will put up something for y'all to be able to work on so you can make sure you can test your ability on that. So from the book only, page 30, 22 through 29 will deal with your in behavior problems. And then there will be a worksheet dealing with the lead coefficient test to determine in behavior that way. If you have questions, make sure you're sending me reminds or sending me emails, and make sure you attach your work to it so I can see what you're doing and what you're talking about. If that is it, then I hope everybody's having a great day, and I will talk to you soon. TTFN. Ta-ta for now.